Lecture number 3, the seasons. We're going to begin by going over 6 factors that work together in interaction that create winter, summer, spring, and fall. So we're going to go over why it's hot and why it's cold and why we have intermediate seasons in between. And the 6 factors begin with the fact that the Earth rotates. And I don't think I need to say anything more about that for now, but that is definitely going to be included in a model that we're going to be making once we go over these 6 factors. Revolution. That is the fact that the Earth is revolving or orbiting the Sun, and it takes 1 year, or 365 and 1/4 days, for the Earth to make one complete revolution around the Sun. And every 4 years, we wind up having an extra day, and we add it to the shortest month of the year, and that's February. That's leap year. The third factor is the fact that the Earth's polar axis is tilted off of a vertical line by an angle of 23.5 degrees. Now, when I introduced the polar axis previously, I didn't mention that the Earth's polar axis was tilted. And this number, 23.5 degrees, this angle of tilt, is going to be quite critical. We're going to see this number again when we do a model of the seasons, once we're finished with these 6 factors. Number 4, the tilt direction is the same all year long. So here we've got the Earth stopped at 4 critical positions during the year. The first day of winter, spring, summer, and fall. And this is a basic diagram of a more detailed model that I'm going to be showing you in just a few minutes. But the polar axis doesn't change. It doesn't wobble or move in an opposite direction. The North Pole is always pointing to the North Star, Polaris. The 5th factor is called the circle of illumination. And what it is, it's a line on Earth that divides it into equal halves of day and night. And so here I added the sun over here on the left, and you can see that one half is illuminated, and that's the daytime. And right here, all along this line of longitude, we call it the noon meridian, that line of longitude, directly facing the sun, it's noon. It's noon here at the South Pole, it's noon here at the equator, and it's noon way up here at the North Pole. All right. So really what the circle of illumination, it's a big term for something really quite simple. It represents that zone of transition from day into night, or on the opposite side, night into day. It represents sunrise and sunset. So if this is noon right here, and the Earth is rotating from west to east, we know that 15 degrees to the east, it's 1 p.m. And then it's 2 in the afternoon, and 3 and 4 and 5 and 6, until we reach sunset. So this right here is representing sunset, and sunrise would be on the opposite side of Earth. So that's going to be included in a model we're going to do. Now, the 6th and final factor is probably the most difficult concept to understand. It's called the subsolar point, and we're going to be abbreviating it SSP. Now, it's a term we're going to be using a lot for many, many weeks. But what it is, it's a latitude location where the sun at noon, all right, is perpendicular to Earth. It's directly overhead. And we're talking about the sun at noon, and that's when the sun is, at its highest in the sky. And when it's at its highest point, it's called its zenith. So we know the sun rises in the morning, and it gets higher and higher and higher in the sky, and it reaches its highest point, its zenith, at noon. Now, the thing is that because the Earth is a sphere and it curves, the sun at noon cannot receive the same intensity of the sun's rays. The noon sun angles are always going to decrease away from where the subsolar point is, because the Earth curves away. So in this diagram, we're showing that the sun is over here on the right, and right at the equator, this is the point, this is the latitude location that is getting the most direct, most intense rays of the sun directly overhead. And this over here on the right is showing you the sun at noon is coming in at a direct 90-degree angle. All right. And so as you move away from wherever the subsolar point is located, degree by degree, the sun angle gets lower and lower and lower and lower and lower until by the time you get to maybe southern Canada, whereas the sun angle was directly overhead 90 degrees at the equator, it's now kind of cut in half. It's only halfway in the sky, 40 or 45 degrees. And then by the time you get above the Arctic Circle, it's only a very, very low sun angle, maybe only about 10 degrees, just barely above the horizon. And this all has to do because the Earth is a sphere. It's curving away from the sun. Now remember, it's noon all along this meridian right here. It's noon. And the sun, cannot present itself to the Earth when it's curving away at the same sun angle. And the important thing about the subsolar point is when you're getting direct rays of the sun directly overhead, or even still pretty high sun angles, near where the subsolar point is, it's the zone of maximum heating on Earth. And we're going to be showing you in the model, in the next diagram, the next slide, that the subsolar point during the year migrates near the bulge of the Earth, between the tropics. So we've got it at the equator, but it migrates to the Tropic of Capricorn in the southern hemisphere and the Tropic of Cancer in the northern hemisphere. And so it's migrating between the tropics, right, near the bulge of the Earth. And, what do you know about the tropics? It's hot there all year long. Right? There's no real winter. And that's because you've got the subsolar point migrating. You've got, intense rays of the sun. And still, if you're very close to where the subsolar point is, you're still getting, high sun angles, 89, 88, 87, something like that. And so you're still getting pretty intense sun angles. Well, just imagine, all right, if the Earth was a flat sphere, what would it be like? What would it be like? All right, if the Earth was just flat like that. Well, every place would be hot. We would be getting the 90-degree sun angles everywhere. And again, because the Earth is a sphere and it's curving away, there's no way at noon that the sun can present itself at the same intensity everywhere on Earth. We're going to move on, and we're going to take those 6 factors and we're going to put them all together in a big model of the seasons. And so what we've got is the Earth stopped at 4 critical positions during its revolution during the year. And we're going to start with the first day of winter, and then we're going to move on to the first day of spring, the first day of summer, and the first day of fall, and then back to the first day of winter. And that's all for the northern hemisphere. It's going to be opposite as you see in the southern hemisphere. So we've got everything here. We're showing the tilt of the Earth's polar axis, and it's tilted in the same direction. We're also showing the circle of illumination. And I want to start with the first day of winter. And these critical dates occur every 3 months. Every 3 months, on or about the 21st of each of these 3 months. So I don't want you to memorize it's the 22nd here or the 23rd here. We're just going to always say that the critical date, or the first day of winter, or whatever, it occurs on or about the 21st of each of these dates. That's what we're going to say. So we're going to take a look at this picture in detail right now, the first day of winter for us in the northern hemisphere. It's called the winter solstice because for us, we live in the northern hemisphere, and it's the first day of winter. The term solstice is Latin, sol meaning sun, stis, status. So we're looking at what is the status of the sun on this date, first day of winter for us in the northern hemisphere. We're saying December 21. So as you can see, the northern hemisphere at its position in its revolution on this date is tilted away from the sun. So it should make sense that since the southern hemisphere is tilted towards the sun, it's going to have a better opportunity to receive the maximum rays of the sun. And indeed, the subsolar point is located in the southern hemisphere. And that's where we're going to have the most intense vertical rays of the sun and still really high sun angles. And so when you've got high sun angles, you're going to have really intense heating. Now, in the northern hemisphere, we're experiencing winter. And, part of the reason is that we're far away from where the subsolar point is in the high sun angles. And so we're getting lower and lower and lower sun angles and not as much heating. Now, specifically, you do need to know this for the exam, that the first day of winter, the subsolar point is located at 23.5 degrees south latitude. Now, it's a very special line of latitude. It's called a sun behavior line, and so it's given a name. It's called the Tropic of Capricorn, and it's in the southern hemisphere, and it's as far south into the southern hemisphere as the vertical rays of the sun can go, the subsolar point. Now, where have we seen this number before? That is the tilt angle of Earth, and so the way the Earth is presenting itself to the sun, this is far south into the southern hemisphere that the vertical rays can go. I mean, say if the tilt of the Earth's axis was 30 degrees, what would the Tropic of Capricorn be? Well, it would be 30 degrees. Yeah. All right, besides sun angle, determining, hot and cold, and another thing that we need to look at is the amount of daylight in each hemisphere. And this is where we're going to use the first factor, rotation. And I want to take a look at really high latitude locations, the Arctic Circle. Now, it's not drawn in here. It is in another slide here. But right here where it's blue along this line is the Arctic Circle. It's another line of latitude, really important one. It's at 66.5 degrees north latitude. And it's called a sun behavior line because on this day, and lasting for about 6 or 7 weeks, the Earth is rotating and rotating and rotating, day by day, and it's rotating through total night, because the circle of illumination and the Earth's tilted polar axis do not match up. And so lasting for about 6 or 7 weeks, it's dark. Can you imagine that? And there are some, a pretty big city. I think there's a city in Russia called Murmansk, population of about 1 million people that have to deal with this. Can you imagine getting up, going to school or work, and not having the sun come out for 6 or 7 weeks at a time? And plus the sun is not out. I mean, that's used for heating. And so it's incredibly cold and really difficult on life. Well, the opposite is going on in the southern hemisphere, where the southern hemisphere is tilted towards the sun. Another sun behavior line is called the Antarctic Circle, and it is shown here as 66.5 degrees south latitude. And then it's add rotation, and you can see that in Antarctica, it's rotating through total daylight, and again, that lasts for about 6 or 7 weeks, and the sun never sets. Now, we're at the bottom of the Earth. Even though the subsolar point is in the southern hemisphere, we're at the bottom of the Earth, and the sun angles are really still low, so they're really not going to do much heating. Sun angle is probably just above the horizon, and what it does is it just rotates around the horizon, day after day after day, and doesn't set. So it's not really giving much heat. But if scientists go to Antarctica, they're going to go there in December when it's summer, and at its warmest, believe it or not. Now, I remember being on Christmas vacation. I was way up here in Aberdeen, Scotland, probably about 60 degrees north latitude. And I remember that the day was really, really short. All right, so if you have short days, the sun isn't out for very long, you're not going to get much heating. And I remember the sun was just about getting above the horizon, getting a little bit bright about 9:30 in the morning. By 10 o'clock, I mean, the sun was out, 10 o'clock in the morning. And then by about 2:30 in the afternoon, you had to kind of finish up your tourist activities, because by 3 o'clock it was sunset. So you can actually see, I mean, there's a long period of night and short periods of daytime. And here we're kind of showing 40 degrees north latitude, a nice mid-latitude location, like the latitude of New York City. And again, you can see, why it's winter. You're not only getting lower sun angles, you're having short periods of daylight, less heating, and long periods of night. So that's the first day of winter. And here's an example, of a high latitude location where where you're really far away from the subsolar point, and this is the sun at its highest point at noon in the sky, and it's only making a very low angle, so you're not going to get much heating at all. All right? So we're not used to that. We're used to seeing the sun much higher in the sky at noon. So let's continue the Earth in its orbit around the sun. And we're going to have the 3 months of winter. So we're going to finish off December, move into January, February, and we're going to stop the Earth at another critical position 3 months from where we began, on or about March 21. It's going to be an equinox situation, and for us in the Northern Hemisphere, it's going to be the first day of spring. So let's take a look at the details now of the first day of spring for us in the Northern Hemisphere. And vernal, it's called the vernal or spring equinox. Vernal means youthful or spring, and occurs on or about March 21st. So for the Northern Hemisphere, we've gone from winter to spring, but in the Southern Hemisphere, it was summer, remember, and so they're going from summer into fall. And what's going on now is that all places on Earth on this day are experiencing equal periods of day and night, 12 hours of day and 12 hours of night. And that's where the word equinox comes from. Equinox, equal night. And in this diagram, showing every place on Earth receiving 12 hours of day and 12 hours of night, is eliminated the tilt of the Earth's polar axis, just to be able to show you that every place on Earth is equal. And I've done a little cutout from the model, just to show you that the tilt of the Earth's polar axis is there. But what they're doing is taking a side view, and they just want to illustrate that on this date, everything is perfectly lined up, and that the circle of illumination is actually cutting right through the poles. And that's what it's illustrating right through here. And so this is an intermediate season. And, what happened is, do you remember where we just were above the Arctic Circle? It was total darkness 3 months ago. It was total darkness lasting for 6 or 7 weeks. Then after about that time, guess what? The sun came out for one day. And the sun was out for maybe 20 minutes, and then it set. Then the next day, the sun came out for a half hour, and then an hour. And then over those 3 months, the sun kept on coming out longer and longer and longer until this day, where the sun is out for 12 hours. Now, conversely, remember that beyond the Antarctic Circle, it was total daylight. But after about 6 or 7 weeks, the sun set. And it set for maybe, again, 20 minutes. And then over those 3 months, the sun was setting longer and longer and longer until we reach this day where everything is perfectly lined up. And we have 12 hours of daylight and 12 hours of darkness everywhere. And the reason why is that the subsolar point is now at the midpoint between the poles. Everything is equal. Now, during those 3 months of winter, this is kind of critical, the way the Earth has been presenting itself to the sun in its orbit, the subsolar point has been migrating day by day from its farthest, most southern location, day by day, and the day it reaches the equator represents the first day of spring, and everything is equal. everywhere, even in Thibodeau. Now we're going to move on to the 3 months of spring. And during these 3 months of spring, the subsolar point is going to be migrating. The way the Earth is presenting itself to the sun, the subsolar point is going to be migrating into the northern hemisphere day by day. And the day it reaches as far north as it possibly can marks the first day of summer. And now, what we're going to be looking at is the exact opposite situation from where we were 6 months ago. Everything is now going to be opposite. Now the northern hemisphere is tilted towards the sun, and we're going to be experiencing summer in the northern hemisphere. And so on or about June 21, we've got the summer solstice for the northern hemisphere. So now let's take a look at the details here. All right. So now we've got the northern hemisphere is tipped towards the sun, and so the northern hemisphere is going to be experiencing summer. Now the southern hemisphere in June is now experiencing winter time. The subsolar point during those 3 months of spring has migrated northward to as far north as it possibly can to 23.5 degrees north latitude. Special line of latitude, the sun behavior line, is called the Tropic of Cancer. Now, let's take a look again at the extremes. Now, 6 months from where we began, above the Arctic Circle, now they're experiencing 24 hours of daylight. So from where we were at the first day of spring, they were experiencing 12 hours of daylight. And so during those 3 months, the way the Earth has been presenting itself, the days just kept on getting longer, from 12 hours to 13 to 14 to 15, until we wind up with a 24-hour day. And then the opposite is true beyond the Antarctic Circle. Remember, the first day of fall for them was 12 hours of daylight, 12 hours of darkness. And so it just started getting darker longer and longer and longer and longer until we reached this date, the first day of winter for the southern hemisphere. And so that's what we were just talking about. And now we're going to move on for the 3 months of summer. Continue the Earth in its revolution, and we're going to finish off June, July, August, and then on or about September 21, 3 months, we're going to stop the Earth in its orbit. And what's been going on during these 3 months of summer, again, the subsolar point has been migrating while the Earth has been orbiting, and the subsolar point has been migrating from 23.5 degrees north latitude back to the equator. And so the day it reaches the equator marks the first day of fall for us in the northern hemisphere. Now, the nice thing about the equinox, spring and fall, is that the situation is exactly the same. Exactly the same. So you kind of take a look at it. It's called the autumnal equinox. We're going to say it occurs on or about September 21. It does vary. And so it's going to represent fall, the first day of fall in the northern hemisphere. So we've gone from summer to fall. And now in the southern hemisphere, it was winter. And so now they're moving into the first day of spring. And again, the subsolar point had migrated from as far north in the northern hemisphere as it could go. And when it reaches the equator, that marks this critical date. And that's where the subsolar point is. And all places on Earth are experiencing equal periods of day and night. Now, we're in mid-August right now. And so this is a critical date that's coming up for us. And we'll be in class, around the first day of fall. And I want you to make note that the days are currently getting shorter. And right now what's going on is, a sunset is getting earlier. Right now, sunsets, I guess about 7:30, and over the next month or so, it's going to be getting earlier and earlier and earlier. And I want you to make note that on the first day of fall, sunset's probably going to be somewhere around 7 p.m. And the same thing about sunrise. Sunrise It's about 6:30 right now. And over the next month or so, we're going to be seeing sunrise getting later. All right, making a shorter day. And so what's going to be happening is sunrise is getting later, and over the next month it's going to be sunrise about 7 a.m. And so pretty much on this date, sunrise in Thibodaux is going to be about 7 a.m. and sunset is going to be about 7 p.m. And so that means that we in Thibodaux, just like every other place on Earth, are going to be experiencing 12 hours of daylight and 12 hours of night. All right. I like to kind of think of where we are in the universe. And so we're in mid-August, and we're in summertime. And I just kind of wanted to show you that we are approaching the autumnal equinox for us in the northern hemisphere, just to kind of be aware of that fact. All right. Now, what we want to do is finish off our orbit around the sun, all right, to complete our year. And what's going to happen now over the 3 months of autumn for us in the northern hemisphere, the subsolar point is going to migrate. And what it's going to do is going to migrate southward. And day by day, the subsolar point is going to be moving during those 3 months of autumn into the southern hemisphere. And when it has reached its maximum farthest location it can possibly go in the southern hemisphere, 23.5 degrees south latitude, the Tropic of Capricorn, it's all related to the tilt of the Earth's polar axis, that marks the first day of winter. So we're finished with that model. This is a pretty neat diagram showing the migration of the subsolar point within the tropics during the year. And so we've got the months, we've got winter, spring, summer, and fall. And we've got the tropics. Here we've got the Tropic of Capricorn, 23.5 degrees south latitude. Now, don't worry about these minus signs. This is just the southern hemisphere. And then we've got the northern hemisphere. And we've got the Tropic of Cancer. Right? And so we're showing the location of the subsolar point during the year. Now, remember we started with the first day of winter. And that's when the subsolar point is as far south in the southern hemisphere as it can go. And then we moved into the 3 months of winter. And during those 3 months in the Earth's orbit, the subsolar point is migrating day by day, right, towards the equator. And on the day it reaches the equator, for us in the northern hemisphere, is the first day of spring. And then during those 3 months of spring, the way the Earth is presenting itself to the sun, the subsolar point, the most intense vertical rays are now moving into the northern hemisphere, and it's getting warmer for us in spring, getting warmer and warmer and warmer. Why? Because the most vertical rays of the sun are getting very close to us. And so on the first day of summer, the subsolar point is at 23.5 degrees north latitude. Very special line of latitude is called the Tropic of Cancer. So I can ask you kind of a stupid question. Now, we know that we're at 30 degrees north latitude, and I can ask you the question, well, does the subsolar point ever reach Louisiana? Well, no. All right, we're located at 30 degrees north latitude, just off of this diagram. And so the subsolar point, we never get direct vertical rays of the sun. But let me tell you, we're pretty close to it. We've got very, very high sun angles on the first day of summer and during the summer months. So the sun angle is at 90 degrees, but it's in the 80s. So we still have pretty high sun angles. And so that's going to give us a lot of heating. All right, so now we're going to continue on during the months of summer. And during the months of summer, the subsolar point is presenting itself. The subsolar point is moving southward back towards the equator. And remember I said, kind of want to mark where we are, in middle August. And from this diagram, we can actually know exactly, where is the subsolar point in mid-August today? We can just kind of move on over from our location in middle August and take a look at the latitude location. All right, I can't really tell exactly, but maybe today or this week when we're doing this lecture, the subsolar point is at about maybe 12 or 13 degrees north latitude, and it's heading away from us. So that means our sun angles are going to get lower and lower, and that means it's going to start to cool down more. And so we're now approaching the first day of fall, and that occurs when the subsolar point is at the equator. And then we're going to move on back, all right, through the months of fall. And that's when it starts to get cooler. And that's why the sun angles are getting really far away from us in the southern hemisphere. And we're getting lower and lower and lower sun angles. And until we have the first day of winter. And that's as far south in the southern hemisphere that the subsolar point, or the vertical rays, most intense rays, can go. So that's kind of a neat diagram. All right. I want to make a conclusion now about the seasons. And seasons, right? Why we have a cold season, why we have a hot season, and then the intermediate seasons. And it really comes down to two things, all right, that I hope that I've emphasized in the model. The first thing is sun angle. If you've got the subsolar point in your hemisphere, you're going to have summer. All right? And what we've got here is a flashlight, kind of representing the sun. And if you can do this experiment at home, just get a flashlight and darken your room and put that flashlight directly vertical, mimicking the subsolar point directly overhead, and you're going to have that 1 unit of sun's rays covering 1 unit of surface area, and you're going to get the full intensity of that of the sun's rays, or the flashlight, and that's not a 90-degree angle. So if you've got high sun angle where the subsolar point is, or even you're just a few degrees away, if you're still getting high sun angles in the 80s or 70s, you're still going to get a lot of heat, and so that's going to create the summer season. Now, if the subsolar point is in the opposite hemisphere, that means it's going to be experiencing winter, and we'll be receiving low sun angles. And let's kind of move to the low sun angle diagram that would represent winter season for us in the northern hemisphere. And they're showing a 30-degree angle with the flashlight. And so you've got 1 unit of sun's rays. Now, because it's tilted, is going to now cover 2 units of surface area. So do this with a flashlight, and you will see that the surface area is much larger, but the intensity of the sun's rays, or the light, is much less. And so you get much less heating with lower and lower sun angles, right? And then the second thing that I was really trying to emphasize when we were going over the model is the amount of daylight. The longer the daylight that you have, the more potential heating that you're going to have. And we've seen that on Earth it can range from 0 to 24 hours. But if you're tilted towards the sun and rotate the Earth, you can see that you're experiencing long periods of daylight during the summer months. And so the longer the daylight, maybe 40 degrees north, latitude of New York City, like I said, we're probably experiencing, my goodness, maybe 16 hours of daylight, maybe more. And so, it's a long period of day, more heating. Now, where you're tilted away from the sun, experiencing winter, well, why is it winter? Why is it cold? You add rotation, and the period of day is much shorter. Much shorter. You're only having 4, 5, 6 hours of daylight, and the shorter the daylight period, the less potential for heating, and so it's going to be cooler. And so, in conclusion, the reason why we have summer, right, and it's warm during the summer months, is because we have high sun angles, That's when the Earth is tilted towards the sun, and the subsolar point is going to be in that hemisphere. And again, since we're tilted towards the sun, we're going to be having long periods of daylight, and those two factors create heating. All right, and then winter is the opposite. That means the subsolar point is in the opposite hemisphere. We're going to have low sun angles, and the sun's rays are going to be spread over a longer area or greater distance. It's much less intense. And if you're tipped away from the sun, you're going to have short periods of daytime and less heating. This is kind of a neat diagram, kind of illustrating, the sun rising, at sunrise, the circle of illumination, and what the sun appears to do during the day, it gets higher and higher and higher in the sky until it's noon. And that is the sun at its zenith, at its highest point. And that's what we're looking at with the subsolar point. And then the sun starts to have its afternoon hours, and then will set and reach the circle of illumination again. And so, I can ask the question, it appears that the sun, is moving during the day, rising to its highest point and then setting. But is the sun really moving? No, the sun is not moving. It's the Earth that is moving. The Earth is rotating. So the Earth is rotating from the sunrise, circle of illumination point, and we're rotating towards the noon meridian. And then we're rotating away from the noon meridian until we reach the circle of illumination representing sunset. But this is kind of a nice diagram representing, this would probably be a good example for what it looks like for us here at about 30 degrees, or kind of any mid-latitude location, say in the United States. This would be pretty much a high sun angle for June, for the first day of summer, and this would be a low sun angle for winter time, kind of in mid-latitude locations. Now, I can ask you kind of a stupid question. Is the subsolar point illustrated in this diagram? No. Right? No, the subsolar point is not. If the subsolar point was illustrated here, all right, it would be directly over the sky's head, making a 90-degree angle. All right, and just kind of going back to this one. No, never mind. Okay, yeah. So never mind about that. But for the exam, you definitely need to know all of your sun behavior lines, particularly where the subsolar point is on those 4 critical days. You need to know the exact degree of latitude and the name, all right? And then the other sun behavior lines, the Arctic and Antarctic Circle, in regards to total daylight and darkness, 66.5 degrees north and south. So you definitely need to know that for the exam. Then I can also ask you, what day of the year is this diagram depicting? Well, the vertical ray is the subsolar point, and, well, obviously, we're tilted towards the sun, and it's the first day of summer, June 21, is illustrated here. And let me just give you another quick example here. The vertical ray here is at the equator, and so we've got 2 days of the year where that occurs. So this is the first day of spring. It's an equinox situation, or the first day of fall. All right, and that ends lecture 3.